Ok, ya sabes, cuando ustedes me digan, si está, no sé si ya esté todo bien, si ya esté todo en línea y todo.
Sí, en principio ya, ¿verdad, Alejandro?
Okay, so I start now. My name is Luis Alberto Razo Lopez, as it's written there. Doctor in physics. I did my bachelor in Guadalajara, in the University of Guadalajara. Then I did a master in physics in la Benemérita Universidad de Puebla, and then finally I moved to the Université Côte d'Azur in Nice, in France, where I made another master and my PhD. I finished my PhD more or less 1 year ago, and currently I'm doing a postdoc in l'Institut Langevin in Paris. So today I will present you part of the research that I did during my PhD, and I titulated my talk as Localization of Electromagnetic Wave Beyond the Anderson Conception. So at the beginning, I will try to introduce what is localization, which is the electromagnetic wave system that we are using, and what is this Anderson conception. So I hope it will be clear. Unfortunately, the name of the seminar is Quantum and Classical Statistical Seminar, and from all the work that I have performed in physics, this that I will show you today are precisely the ones that are not related to with statistical stuff. But anyway, I hope you will enjoy, you will understand something. And if you have some experimental proposition that you think that it can be performed in this setup that I will present today, you can come and we can discuss about the particular realization. So let's start. First, I like to start with this slide to put some examples. For example, when we listen some music or when we see some lights in the street or something, or for example in Mexico, so overall the people that come from Mexico City, if you have had the bad experience to feeling an earthquake, it is easy to relate wave phenomena with a propagating event, something when the waves propagate freely in the space. This is because all these examples has a continuous dispersion relation. What does it mean? It means that for any frequency, we'll have a wave vector that will propagate the energy. But having a continuous dispersion relation is a particular characteristic of homogeneous media. However, is it well known that considered inhomogeneous media, structured media will introduce some discontinuities in the dispersion relation. What does it mean? That for certain frequencies, we'll have a band gap. That means that in the practice, if we send a wave to this medium, we'll have some transmission that will be close to 1 and reflection that will be close to 0. No, reflection close to 1 and transmission close to 0. Yeah. So these examples of structured media exist in all the dimensions 1, 2, or 3, but unfortunately they are mostly in fabricated materials or artificial systems, and this is not what we find in nature. What we find in nature, it's a partial structured media. For example, structured materials are the responsible of the blue colors in the wings of the butterflies, of the color skin in some mammals, the skeletons of the insects, of some birds' feathers. Additionally, they are also the responsible of the transparency of the retina and the white color of certain beetles. Particularly, some years ago, some people tried to characterize all these different behaviors of the wave with respect to the correlation, or what's the opposite of the correlation of the particle, the disorder of the system. So they created this diagram that I'm showing you when they explain they found transparency, diffusion, band gaps, all of them as a function of the frequency and as a function of the order of the material. And particularly, they also find another uh, how to say, I forgot the word, another transport regime called Anderson localization. So what is Anderson localization? Anderson localization, it's a regime that happened for completely uncorrelated disorder. What does it mean? A system that is completely random. And what is called Anderson localization? So let me show you what Anderson found. Anderson considered first the tight banding formalism. I suppose most of you can be familiarized with this, but otherwise, anyway, I will explain it. So a tight banding system, it's a system of sites that are coupled by some energy. So, for example, if we consider that V, that it's this that we observe here is a typical equation of a tight banding formalism, where T is the coupling and V0 is the eigenenergy of the site. So, for example, if we consider both T and V as a uniform, we have extended states. That means the waves are completely extended in the system in all the sites. So what Anderson demonstrated is that by adding uncorrelated disorder, now the waves are no longer extended, the states are no longer extended, but exponentially localized in certain sites. So this phenomenon has been observed already, for example, in cold atoms, and also in some classical systems like ultrasound or microwaves or photonic lattices. But there has been an extremely long debate about what's happened in 3D media. And it has been very recently, at the end of 2023, that finally 3D Anderson localization in electromagnetic wave, 3D in electromagnetic wave has been finally predicted. So what I will show you today are this kind of system with Anderson localization, and not precisely with Anderson localization, but other kinds of localization. So to characterize Anderson localization or other kinds of localization, we use a quantity, for example, called tallest conductance. And what's the tallest conductance? It's a quantity that is defined between as a ratio between the distance, the mean level spacing between distance and the width, the mean level spacing and the width of the resonance of the system. So, for example, in a system when the resonance are extremely wide and this width of the resonance is larger than the mean level spacing, then the states can couple among them, and we are in the conducting regimes. In the other case, where the mean level spacing is much larger than the width of the resonance, we are in the localized regime. So going from one to the other by adding disorder is what we call the metal insulator transition. So as we observe, all of them are in this diagram: transparency, diffusion, band gaps. So what we'll talk about are systems that are not disorder. So that's why I said that we will go beyond the Anderson conception, because we won't talk about precisely of Anderson localized system. We will be in systems that are completely organized, but that still present some localization. So, for example, one of them is a system that presents the absence of conductance, but with extended states. And the other, it's a perfect conductor, but with well-confined states. So let's start by this first. So to show you this, I need to introduce a little bit more theory. So let's start by discussing what is an topological insulator. A topological to understand what is a topological insulator, first let's understand what is an insulator. which is a traditional insulator is a system that it's isolating everywhere. So normally they are characterized by having two bands separated by a gap. A topological insulator, it's similar in some sense because it's a system that it's isolating in the bulk, but has a conducting surface. So they are characterized by having band gaps, two bands, and separated also by a band gap. But now the band gap it's populated by the conducting state. So to characterize them, there are some topological invariants. For example, the Chern number. In the traditional insulator, the Chern number is equal to 0. In the topological insulator, it's different to 0. And this number also indicates, for example, in the case of the Chern invariant, the number of H states that we have. We have different kinds of topological insulators. For example, the most common is the one that we call that is related with the quantum Hall effect. That it's a topological insulator that characterized by having a time reversal symmetry breaking, and we have H states in this case that are called chiral, propagate in just one direction, and they are immune to backscattering. Why? Because the state that propagates in the opposite direction doesn't exist. Another kind of topological insulator that we can have are the ones that preserve time reversal symmetry, that are called or related with the quantum spin Hall effect. In this case, for example, we can think as two shared insulators with opposite spin. So we have a Chern constant equal to 1 in one of them and equal to -1 in the other. That gives a Chern constant equal to 0 in total. And in this case, we have one state that propagates in one direction, another that propagates in the opposite direction, and we need to idealize another topological invariant that will characterize this system. For in this case, is the C2 topological invariant, and this the kind of H states that we find here are called helical states. So we will start by this system, and I will show you how we will do to arrive to our electromagnetic representation. So to that, we will consider a honeycomb lattice, and the typical conception of a honeycomb lattice is to consider two sides per unit cell. I'm showing you here, where A1 and A2 are the lattice vectors. So then we have an hexagonal brilliant zone that gives a band diagram with a Dirac point in K. So what we will do now is to change a little bit this vision, and instead of consider two sides per unit cell, we'll consider 6 sides per unit cell. So as we can see, the lattice vectors A1 and A2 are quite larger than in the previous, and that results in a brilliant zone that it's smaller. As we don't have any loss of information, so we need to have exactly the same information in the band diagram. We observe that the bands are fold, and now the Dirac point, it's not at K, but at gamma. So this is another characteristic of this system is that it has a symmetry called C6. That means that if we turn our system in an angle of 2 pi over 6, we will obtain exactly the same system. And this symmetry is quite important because if we solve the eigenfunctions of one cells, we can divide, or we will have six different states that are S, P, and D, and even F states. And using particularly the two states that are in the center of the band at zero energy, we can get some linear combination, P plus, D plus, P minus, D minus, that are related with some pseudo spin, some quantity that it's turning around in the cell. So this, for example, if we measure the the distribution of these states P plus and D plus and P minus and D minus, if we project in the band diagram, what we observe that they are quite well separated. We have in the upper band P states and in the bottom band the D states. So now with this example, I will introduce another advantage of considering 6 sites per unit cell. And it's that now we can play with the coupling inside the cell and outside the cell. So for example, in this case, this example is for T1 equal to T0. That means that the couplings inside the cell are exactly the same that the couplings outside the cell. But what happens if we change the division? If we make the cell a little bit more smaller, so we have a stronger coupling inside the cell than the coupling outside the cell. So what we observe is that we have a band gap. Nevertheless, the distribution of the pseudo spin up and pseudo spin down, I mean P plus, D plus, and P minus and D minus, is exactly the same. However, if we consider the other case, the case when T1 is larger than T0, now we have an inversion of the band. And this inversion of the band is one of the signatures of having a topological system. So for example, if we compute now the topological invariant, we observe that this C2 invariant is 0 in the 2 first examples, while in the third one, it's equal to 1. So we confirm that we have a topological insulator. So to observe, for example, now the H states, we need to consider a system that is that has some boundary, a system that is topological in one region and then not topological, or what we call trivial, in another region. The problem is that this C6 symmetry that it keeps for this turning of the complete system. What happens if we suddenly cut the system? That we destroy the C6 symmetry. So to induce to observe conserve the topological state of the system, the topological behavior of the system, we will introduce a smooth breaking of the C6 symmetry. So to do that, instead of simply put the system with the vacuum, we will put the system with some the topological system pasted with a trivial system. That means in one region we'll have the coupling of outside the cell will be larger than the coupling inside the cell, and in the other will be the opposite. The coupling inside the cell will be larger than the coupling outside the cell. So if we do that, we can measure the currents in the currents that go from one side to the other, and we can observe that we have these helical states that propagates unidirectionally. So this is an important point to stop and remind that these H states that exist in topological invariants are not a surface effect, but a bulk effect that will manifest in the H. What does it mean? It means that if we have a system of certain size and then we cut a part of the system, the H states will move to the new boundary. They won't disappear because they are not part of this boundary. They are part of the complete system itself. So let me show you now how we will measure. Let me introduce the experimental setup. So the experimental setup that we use to measure these topological states, it's composed by 2 aluminum plates. As I show you here, this is a photo of the setup. And one of the plates, the bottom one is fixed. The top one is attached to a XY stage, so we can move freely in the XY direction. In addition, each of these plates are connected by some antennas to a VNA. And what's the VNA? The VNA, it's an scattering matrix. It allows us to measure the scattering matrix. That particularly will be focused in measure S21 and S11. That means the transmission between one antenna to the other and the reflection between the antenna that is in the top plate. That means the antenna that can move freely. Our system will be measured by some antennas that are loop antennas, like I show you in this photo. And what's the particular of these antennas? That they introduce a T polarization. That means that the magnetic field it's perpendicular, parallel to the normal vector of the surfaces. Our system will be made by by these cylinders, that there are dielectric cylinders that are, as you can see, they have a high permittivity, 45. That means a refractive index of 7. They are quite small. And what's the particularity of these cylinders and this particular polarization is that for this polarization, the electromagnetic wave cannot couple with the air. That means that they are evanescent at frequencies below this cutoff frequency of 12 gigahertz. But they can still propagate inside the cylinders. As a result, the energy is confined inside the cylinders. So what does it mean? It means that for each cylinder, we will have a very thick resonance, as I show you here, that it's around 7.4 gigahertz. We will measure between 7.1 to 7.7. But the particular stuff occurs when we put, for example, two cylinders together. So if we put two cylinders together and we start changing the distance between these two cylinders, we observe some splitting in the resonance of both cylinders. That, as you should know, can be modeled in a Hamiltonian of two particles that are coupled. We can actually characterize this coupling with respect of the distance, but the important part is that we can emulate the theoretical system, the theoretical model that I showed you at the beginning, when we have a honeycomb lattice with two different couplings, where now the distance will be play the role of the couplings, and we can create or setup or lattice as we want. So we will do that. We will arrange our cylinders in this way, in the same way that the theoretical setup, and experimentally it looks a bit like that. We use approximately 400 cylinders, and we will have two different materials. One material that it's topologically trivial, and another that is topologically not trivial. That means the one that expects the topological behavior. And we do that because we want to observe these eigenstates. So as I mentioned at the beginning, the fact of cutting the system suddenly should kill the C6 symmetry. So that's why we put this, we create this interface between both systems. But then in addition, we will measure each system twice by changing the bottom antenna. Why? Because we have one helical state that moves in one direction and another that moves in the other direction. So by changing the position of the fixed antenna, we can try to measure both helical states. So let me show you one example by looking just at one of these systems. So for example, what happens if we look at a site that is in the trivial bulk? So we obtain a signal like that. And what we can observe is that around 7.4, we have the transmission that goes close to 0 and the reflection that goes close to 1. That is the signature of the bandgap that we already discussed. The other case, for example, if we look now a site that is in the bulk of the non-trivial system, we observe a very similar signature. another time a signature of a band gap. But now, if we look aside that it's in the interface, we have a completely different stuff. Now we observe that the transmission has extremely higher values with respect to what we have previously observed. So let's make a little bit more deep the analysis of this data. So first, let me show you how we can extract the density of state for the reflection measurement. This, it can be so easy because the local density of state, it's already related for a very easy relationship with the reflection measurement of our system. So the complete density of state can be just obtained by averaging over all the position. And what we observe here, what we observe in this case is this. So here I'm showing you the density of state as a function of the frequency and as a function of the deformation. What does it mean, the deformation? It means that we start for a system that it's a perfect honeycomb lattice, and then we start changing the size of the hexagons for going for a topological region. So we observe a band gap that start opening, but this band gap, I don't know if it's clear for you, because I don't know how is the quality of the transmission, but it's not completely white. It's not completely clear that we have a band gap, but this can be solved because thanks to our definition, we can define a partial density of states, a density of state that taking counts just the sites on the bulk of just the sites on the edge. So by computing this partial density of states, what we obtain is this. First of everything is that by looking the density of states of the bulk, we can observe that now we are going really to zero. So that means that we have a band gap around 7.4. And in the other case, the density of states of the edge, we observe that we have something completely different than zero. That means that we have no band gap in this case. And as a conclusion, we can say that we have some states that live in the edge of the system and whose energies are in the band gap. So now we'll try to measure this pseudo-spin propagation. So this is so simple because the pseudo-spin can be completely mapped in an electromagnetic system to the electromagnetic angular momentum of the cell. So to do that, as I mentioned before at the beginning, our setup is we measure in the frequency. So to measure the propagation, we'll perform a Fourier transform. That means we'll take the signal, we'll filter the signal, perform a Fourier transform, and we'll obtain the transmitted signal of a pulse in time. So now, from this transmitted signal, we'll compute the angular momentum using the Poynting vector that, to save all the maths, reduced to this expression, and we will compute this quantity for any of the sites that we have in our system. And what we obtain is this. So let me show you this movie. In the left, we have the antenna in the upper part. In the right, we have the antenna, the bottom part. Here, there are different information. First, the color defines the spin down or spin up, and the intensity defines the intensity of the spin. So what we observe here is that when the antenna is exclusively in the top, we have the one of the pseudo spins that propagates in one direction, complete unidirectional, and in the other case we have the other spin, the green one, that propagates in the other direction. That is precisely what we were looking for. So to synthesize this, we can integrate in time, and we have these diagrams, these propagating diagrams. The interesting part is that when we measure when we perform this analysis for different frequencies, what we observe is that we also have the propagation between the topological material and the vacuum, which wasn't technically not expected by the theoretical model. And this was quite surprising, and it's actually quite impressive that our system still keeps this kind of characteristics that are not predicted. As we can see, each of the state propagates a different frequency. This is just is just response of the boundary conditions, of the different boundary conditions between having one material, one boundary between two materials, and the boundary between the vacuum and one material. So now the other stuff that we did with these helical states, it's try to measure the velocity they propagate. So to do that, we labeled some cells in the interface, and we measure the maximum, not really the maximum, we'll measure actually the barycenter of these poles that we have, and we observe the velocity the pulse propagates along the system. And what we observe is that this velocity, it keeps more or less constant for different deformation. That means that it doesn't really matter if we deform the cells too much or we just make a small deformation, the velocity is more or less constant. And in addition, we observe that this is exactly the same velocity that we observe for the group velocity. That means the velocity that the pulse propagate in the system. And the most surprising is that also if we try to model this system as a complete in a tight banding modeling of a ribbon semi-infinite system, we compute the band diagram of that system, and we see the group velocity. It's more or less the same. It's quite well. It fits quite well with what we had measured in the experiment. And not only that, also if we if we consider just a mechanical chain of 1D mechanical chain of harmonic oscillator, and we measure once again the group velocity, we observe that it's approximately the same. That means that our helical states now to this system propagates in just one direction. That means it's just a surface effect, as we extend from the beginning. So the last part of this first half of the talk, it's what happened if we induce some defect in the system. So now we propagate, we do the same experiment, we launch some wave, we observe how they propagate, and we observe that they will turn, they can turn through the defect, or they can also tunnel. Actually, from the experiment, it's not too clear to see. We observe that at least part of the wave it's turning around, but other part it's also tunneling. And now we observe, for example, now the evolution of the pulse with respect to the time for the two particular cells that are before the defect. And what we observe is that all the propagation keeps the sign during all the time interval. That's important because what we are concluding from this is that this defect doesn't perturb the unidirectional of the unidirectionality of the transport. That means that one pseudo spin will propagate always in the same direction. Doesn't really matter if there is this defect or not. So until now, I showed you this topological system, that it's the system that has the states that are localized in the boundary, and that has a very huge transmission. And now I will show you the other part, the systems that has the absence of conductance, but with well-extended states. So for show you this, I will introduce you what are this particularly array of systems that are called Vogel spirals. So Vogel spirals are well known in nature because actually it's the way that the sunflowers grow, the pine cones, agave, or Romanesco cauliflower, and they are quite easy because to define them, we use the polar coordinates. So we have the radial coordinate and the angular coordinate, where this alpha is peak irrational. So, for example, in the case of of the system that we will talk in we will discuss now, it's the sunflower spiral that has alpha equal or approximately to 2.4, where this 2.4 is also related with the golden mean. That's why it's also called golden spiral. I jumped too fast to this slide, but it's not a problem. What I wanted to show you to say before is that there are many works that have been performed in Vogel spirals, and now I will focus a bit in the works of light propagation, but in this kind of system. So I want to talk about three different works. The first of them is this, that consider, it's a numerical study that consider a system of it's a dielectric with holes, air holes. And what would they observe here? Before saying what they observe, it's important to mention that now we are not talking about a tight banding system. This model of sites that are coupled to other sites, it's not valid here anymore. Here we'll have a wave that it's propagating in a system and it's being scattered by the defects of the system. So here they have this dielectric that has these holes. The wave can propagate freely, and what they observe is that this particularly a range of points induce a band gap. So here in the density of states, we observe a decay of the density of states approximately a 0.3. And as a conclusion, they say that the correlation induced by Vogel spirals create a band gap. The next part of this work is to find the eigenstates, and they found this particular eigenstates that are well extended, that follow the shape of the spiral, and that are particularly exist particularly with energies in the borders of the band gap, in the edge of the band gap. The second word that I wanted to show, it's this word where they don't consider a dielectric, they consider actually a 3D system. In this 3D system, they make a planar array of points, a planar array of this Vogel spiral, and they study the behavior of the wave in this 3D system. So what they find is that they found exactly the same states, but the more surprising, the counterintuitive part of this work is that they find some conductance that are quite small. That means that states are localized in this 2D array of points, and are precisely these states that follow the shape of the spiral and that are well extended, the ones that presents the smallest, tallest numbers. That means the states are more localized. And the third work that I wanted to discuss before showing you the experiments are states that characterize it's a work that characterizes the states of this that we find in these Vogel spirals. So we observe that there are some kind of states that are Gaussian radial states. That means these states that follow the shape of the spiral, they have a radial behavior, but we also have some exponential states that are like the ones that we found in Anderson systems, and others that are a power low radial decays that are radial states that are called critical modes. So what I will show you now is how we can measure this in our system. So we'll come back to the same system that we have, but we will add an important element, that is this hydraulic lift. And what it's important is because this leaf will allow us to change the distance between the two plates. So now another stuff that will change is the kind of antennas. Before we have some antennas that were loop and induce some transverse electrical polarized wave. Now we have a TM, transverse magnetical. So now the electric field is parallel to the normal vector of the plates. And the new of the difference between these antennas is that they can couple this wave can couple with the air at any frequency, and particularly we will have different behaviors respect with the distance between the plates. In this case, the cylinders are not the sides of our tie banding system, are scatterers, or more properly said, resonators. So the different behavior that we will have, it, for example, at low frequencies, we will have that the waves that can propagate between the two plates are completely homogeneous in the z direction. That means our system will be completely homogeneous in this direction and will behave as a completely 2D system. However, if we start increasing the distance between the plates, we will start propagating the second and third mode, and the electric field, it's not homogeneous anymore. So now we have different behaviors, and this is not a 2D system, it's something beyond. We don't like complete to call it a 3D system because we still have the two plates that are restricting a bit the dynamics, so we say 2D plus. Now we will study a frequency range between 5.5 and 15 gigahertz that will allow us to see this behavior in the dimensionality. So the system that we will construct build this time, it's also with the same dielectrics. We will also use around 400 cylinders, and it has a radius of approximately 14 centimeters. So now, as the wave can propagate everywhere, we won't measure just in certain points. We will measure in all the systems. So we have approximately 4,000 measuring points. And for instance, if we observe a measurement at 10 centimeters from the center, what we observe is this. And what we can see first is that we have the same behavior of a band gap that we already observed before. That means transmission close to 0 and reflection close to 1, at least in two parts, around 9 gigahertz and around 11. And this is important because, as it was already predicted, localization happens around the band gaps. So that are important sites to look out. So one of the quantities that we will be interested to compute is the tallest conductance. That, as I mentioned, it was the resonance width over the mean level spacing. So in an experimental system, the frequency width will be given in terms of the time decay of a certain pulse in the system, and the mean level spacing will be given in terms of the density of states. So first, to compute the decay time, we will consider one more time the transmission signal. We will perform a Fourier transform, and then we will sum over all the sites to get the energy. So we'll have a beautiful plot like that. That is the energy as a function of the time. Here in the bottom part, we can see the pulse that we are inducing in the system to get this energy, and we observe a beautiful exponential decay. So by characterizing this exponential decay, we can extract the decay time. That, by repeating this process along different frequencies, we can obtain the decay time as a function of the frequency. This plot by itself is not so interesting, so I will come back to it a little bit later. So now the density of state. The density of state will compute it exactly as we did before, and by averaging the reflected measurement over all position. And what we observe from the density of state first is that if we set the plates at a distance of 13 millimeters, when this black line, vertical black line, mark the transition between the completely 2D regime to the 2D plus, we observe that we have two band gaps. One of them, it's a little bit coated by this line, but we still observe a band gap, and we have a depth fall of the density of state around 6.5. What happens if we change the distance between the plates? The first stuff is that the second band gap completely disappeared. We observe that the second band gap doesn't exist anymore, and the first band gap has reduced its width a little bit. So now, if we increase a little bit more the distance between the plates, the second band gap doesn't exist, and the first band gap has reduced even more. So what this demonstrated is that the presence of the band gaps depends completely on the dimension of the cavity that we can play with. So now we can compute the tallest conductance with these two quantities that I showed you, the density of states and the decay time. So if we observe the tallest conductance, what we observe is this. We have this line around 1, and we observe that we have plenty of regions when the conductance is larger than 1. That means we are in the conducting regime. But the most important is that we have all these peaks, particularly around the depth that we already observed, and in the edge of the band gap that signalize localization. So, for example, this is for 13. So now if we can compute for 15 or even for 17, we observe a tallest conductance that is quite similar. Despite that for higher frequencies, the tallest conductors start increasing and increasing. That means that we are more and more conducted. We still have regions that, for example, in the lower edge of the second band gap, where we observe a decay of the tallest conductance even for 70. That means we are in a system that is no longer 2D, and we still have this strong signature of localization. So these are the systems that these particular frequency regions when we expect localization, and are the regions that will we try to look into. So to study this kind of localization, we need to see the kind of states that we are looking. So let me show you, let's stop a bit the physics to show you some numerical method to find the eigenstates. So, for example, to find the eigenstates, what we do is something called harmonic inversion. So we take a part of the transmission spectrum, as we can see here, and we will apply, we will first use the Wigner-Bright decomposition. That means that we will express this transmitted signal as a sum of complex Lorentzian, and then we will apply this harmonic inversion that will provide the 4 parameters of this Lorentzian. That means the amplitude, the frequency, and the width. I say 4 because the amplitude is complex. So we have amplitude and intensity and phase in the amplitude. So if we apply this method to our signal, for example, the signal that I'm using as example here, what we observe is this. This pink line is the original signal. The blue line is the recovered signal after applying the harmonic inversion. And each of these lines that we observe in the imaginary part are a resonance that we are extracting. So there are quite a lot in this example. So if we do that for a certain region, certain frequency region, and one position, what we observe is this. We will have different quantities. Here I'm plotting both. I'm plotting all the amplitude, the width, the phase, the position in X and the position in Y as a function of the frequency. So we have these points that I'm showing you here. So if we repeat this as a function for all the position, what we'll have, it's a big map like this one. When we start we observe some cloud of points that start appearing. So if we selected this cloud of points, some of them were delimited, what we observe is that actually we can recover these clusters of points are related with the modes of the system, the eigenmodes of the system. I mean, I call eigenmodes, but they are the quasimodes because we are in a propagating system in this case. So now let's see what happens if we look into this region that we're interested. If we look first into this, the band edge of the band gaps, we observe that we have these Gaussian states, these states that follow the shape of the spiral and that has a Gaussian decay. And we can observe that we have a huge quality factor. What's a quality factor? The quality factor is defined as the frequency of the state over the width of the state, and it measures the quantity of energy that the state can have in some sense. But not only this, if we observe the other part, a lower energy, we observe also the power law decays, the power law decay states and the exponential states, all of them with huge quality factor. These states that I'm showing you here are just the states for the case of 13 millimeters. But what happens if we change the distance between the plates? Let's focus in this case, in the case of the Gaussian decays, where both the 15 and the 13 on the 70 millimeters distances systems are not longer in the 2D regime. So what we observe is this. We observe that by changing the distance between the plates, the states keep the same shape, as the same frequency, and a very similar quality factor that is still very high. There are another important point that I like to mention about this result, and it's that from the first measurement, that means the state in the completely 2D system at 13 and the two measurements at 15 and 17, we move the lab. We were in a certain place of the city, the lab or the lab with our offices and everything, and we moved the lab to another part of the city. So we destroy the experiment, we put the experiment in the other lab, we redo the experiment, and we still observe this strong characteristic of the system. That means that it's not a casualty we observe this, it's something really robust that we are able to measure. So this what proof is that the Gaussian states are robust to the dimensionality change beyond 2D. The last part of the talk is that I want to show you is what happens when we induce some disorder to the system. So we observe that these states are robust to the dimensionality change, but what happens when we induce disorder? So here I start at R equal to 0 to the perfect lattice, and this R means how much I'm moving the sides with respect to the original position. So at R equal to 4, we observe that the lattice is completely disordered. And we will perform the same analysis, but just for a small window that consider these Gaussian states that are robust that we already observed. So what we observe for the density of states and the tallest conductance is that both the band gap disappears approximately at 2 or 3 of the radius of disorder, and also the tallest conductance. The tallest conductance, this low peak that we have below, it disappears approximately at 2. And if we observe the evolution of the states, we observe quite the same. We observe that we have our Gaussian state at the beginning, that it's quite beautiful. Then we start adding disorder, the state start to deformate until the point that we can no longer recognize this shape of the spiral. And actually, if we take this state, the most disorder, and we measure the radial decay, is not longer Gaussian. Now it's exponential, as the ones in Anderson localization, but the localization length is quite large. It's larger than the size of the system. That I remind you, it was approximately 140 millimeters. So we have almost twice. So this state is not localized. So what I like to say before concluding is that these correlations in Vogel spiral are crucial for the localize of the modes that don't exist when we induce disorder on the system. So to finally conclude, I show you two different systems. The first of them is the topological insulator that are characterized by having these highly conducting modes that live in the edge of the states and in the band gap, that are characterized by some topological invariant, and these states propagate unidirectionally. From there we are able to measure the pseudo spin velocity that actually it's the same that the group velocity. The other are these Vogel spirals that have a different variety of states, of localized states, these Gaussian states, critical modes that are the power law, and the exponential ones that present a small Tolle conductance. That means that they are quite localized, despite that they are extended. These states, particularly the Gaussian, are robust to the change between 2D and 2D plus, to 3D if you want to say, and this localization disappears when we add disorder. That means that it's proper to this particular array that we are creating. So here in this QR code, we can find the papers related with these works, and also the link to my PhD thesis that contain also this a little bit more details about these examples. Thank you so much.
Thank you, Russell. Some questions? No, we are. Some good. Can you hear me?
I can hear you, but not so perfect. I don't know if you can come close to the micro.
I have just two quick questions. So is it known in the case where you have the honeycomb lattice, how robust are the edge states to the coherence? You can have a little bit of disorder or chop the edges, and you can still have these helical states or this boundary correspondence. But what happens if you have the coherence? Is it still robust, or is it easily lost, this property of the states?
Well, the states propagate precise frequencies. I mean, at the end, when we observe the band diagram, they can be quite isolated. So if we are a little bit decoherent in this sense, it's not so important until we start mixing with the bulk states. At this point, it's not that they doesn't exist, is that they will also couple with the states that are inside the bulk. So we will observe a mixture of everything, and not only the edge states, but they can be, I don't know if they can be robust, to be honest. Something I still I need to think. I'm not completely sure.
So it was just like a general curiosity if the people in the community usually ask this type of of
Yeah.
approaches.
Yeah, no, it's something I need to think a little bit deeper. Not completely sure. Thank you.
And the second, which is a little bit connected,
Mhm.
who are responsible of arranging 390 cylinders in the table?
Me, and actually, I don't know if you notice, it's quite more than that, because for the first experiment, the topological experiment, we perform for different disorder, for different, not disorder, for different size of the states, of the cylinders, of the hexagons. So I arranged quite a lot, but I have to say that it's quite simple. Why? Because the same system that we used to measure, instead of putting the plate, we remove the plate, we put like a pipe. So we just tap, we put the map, the map of the cylinders into the computer, and we go one position, we put one position, we put. So it's not so slow. Actually, for pouring this 400, it's less than 1 hour of work.
Okay. Thank you very much.
You're welcome.
Another question?
No.
Joe? ¿Alguien question, Alejandro? Sí.
Tiene hora de broma.
Desde Francia. Sí. Bueno. I guess there are no questions in YouTube. Thank you, Rosa, for your presentations.
You're welcome.
Thank you very much.
Let's stop here.